Hi, and welcome back to our video series here. We're still doing the introduction. Today we're going to talk about sets and set operations. Again, most of what is in this video will probably be familiar to you. The idea is mainly to harmonize our notation so that we all mean what I intend to convey by using some specific notation here. Okay, so this is the part of the introduction titled Sets. Again, we're not going to really define what a set is. Actually, that is, mathematically speaking, that is a pretty hard question. But most of what we are going to talk about is built on some understanding, some intuitive understanding of sets. So for the sake of this class, a set is some well-defined collection of distinct objects, which are called elements of the set. Yeah, so there is some definition that uniquely determines which elements are contained in the set and which are not, and all the elements in the set are distinct. No two equal elements can be in the set at the same time. So a set is a well-defined collection of distinct objects which are called elements. Of the set. There is a simple notation for denoting whether some number, some object is contained in the set or not. That is the element in notation. So we write something like an element A is contained in a set A if A is an element of that set. And of course, there's also the non-element notation. So A not element of capital A otherwise. Okay, so each element is either contained in a given set or not. There's one special set, set with no elements at all, that is called the empty set. And there's a special notation for the empty set. So the set with no elements is called the empty set. And denoted by the notation looks like this, a circle and then a slash through that circle. So this denotes the empty set. Well, when are two sets equal to each other? Of course, we just compare their elements, so two sets are equal if and only if they contain exactly the same element. Two sets equal if and only if they contain exactly the same elements. And of course, we can count that number of elements in a set as well. A set can have a finite number or an infinite number of elements. And to denote the number of elements in a set, we use what is called the cardinality. And again, there's a notation for that. So the number of elements of a set A is called its cardinality, and denoted by A in absolute value signs, like this here. For a set that doesn't mean an absolute value, that wouldn't make much sense, that refers to the number of elements, the cardinality of a set. One other special set that is defined for every set is a so-called power set. The power set is simply a set of all subsets of A, and of course, to define that properly, we first have to say what a subset of A is. So for two sets A, B, we say that A is a subset, or similarly a superset of B if each element of A is also contained in B for the subset, or if each element of B is also contained in A for the superset. The notation for this we usually use a notation like A subset of B, like this. And that means I'm also including equality here. I'll usually have that implicit. Or you can also use a notation A subset of B without that equality sign. In this course, those two notations will mean exactly the same thing. So equality is included in both cases. If I want to exclude equality, then I will specifically write this. So to exclude the equality case, we write something like A is a subset of B, but not equal, like this. Yeah, you could also say A is a proper subset of B. And of course, for supersets, the notation is similar here. A is a superset of B, would be denoted like this, by just turning that sign around. Yeah, or without the equality. And now we can finally define the power set. And that simply is the set that consists of all subsets of a given set. So a set of sets. The power set of a set A is the set of all subsets of A. And this includes the empty set, and it also includes A itself. Notation, the power set is usually denoted by the notation 2 to the A. Now that might seem a little strange. That's what I'm usually going to use, There's a similar notation, a P of A, yeah, with a script like P, like this. Maybe you're used to that one. It doesn't really matter which you use, both are fine. Okay, we've talked about sets, we've talked about relations of sets, so subsets, we've talked about the power set. Now it's time to work with those sets. So next topic, set operations. And there's basically 3 operations that you should know. Of course, the union of sets is one. So if you have 2 different sets, you can throw them together to form one larger set that contains all the elements. Then there is the intersection. So again, for 2 sets, you just take all the elements that are contained in both of these sets at the same time. And then there is the set difference, meaning you have one set and you take all the elements from that set that are not contained in another set. So you remove this other set. It's a set difference. Okay, let's write that down. First thing is the union, denoted as A union B, of 2 sets AB is the set that consists of all elements that are contained in A or B or both. It's not an inclusive union, an exclusive union, it is an inclusive union. Then there is the intersection. The notation for this is A intersecting with B like this. Of 2 sets AB is the set that contains all elements that are contained in A and in B. And finally, the set difference denoted by A without B, or A less B, of 2 sets AB is the set that contains all elements of A that are not contained in B. So you remove all the elements of B from the set A. That's what's called the difference. And finally, one more operation that you might not be familiar with as of yet. That's a so-called Cartesian product or set product. And it's denoted by A times B like this. Of 2 sets AB. Now that set does not consist of elements in A and or in B, but instead of new elements, new kind of elements that combines those from A and from B. What we have here is that set consists of tuples, meaning you have a first and a second element in that tuple, and the first element is from A, and the second is taken from B. So this is the set of all tuples. Of the form AB. Now tuples are usually written this here, where A is an element in capital A in the set A, and B is an element in set B. And you just form all possible tuples, all combinations of elements, and that is the Cartesian product. Okay, so in other words, A times B is defined as, and if I write down a definition, if I define something, then I'm often using this notation here with these two dots here. That means this is a definition. The term on the left-hand side is defined through the term on the right-hand side. So it's not a claim that these are equal, but they will be equal by definition. I define them to be. Okay, so this is a set of all tuples of a form AB with A in A, B in B. Then there is a slight abbreviation if I take the Cartesian product of a set with itself. Also, I can do that. I can form tuples that consist of elements of one set only. Then I abbreviate that by just writing A squared, A to the third, A to the fourth, and so on. So we abbreviate A times A as A squared, A times A times A as A to the third, and so on. Now let's see a quick example to clarify this notation and all of these notations. We'll work with two sets. The set A shall consist of the numbers 1, 2, and 5. And the set B consists of the numbers 0 and 1. Now the cardinality of A clearly is 3, has 3 elements, and that of B is 2. For the power set, we just do B, so 2 to the power of B. What is that? Well, the power set contains all subsets of B. So there are subsets with no elements at all, the empty set. Then there are subsets with just one element, the set 0 and the set 1. And finally, there are subsets with 2 elements, and that's the set B itself. Okay, there's no larger subsets, obviously, so this is the power set of B. And notice that this set here, the set containing the element 0, is not the same thing as the empty set. This here has one element, the number 0. The empty set does not have any element. Okay, let's do some set operations. We could take the union of A and B, for example. So we take all elements that are in A or in B, and that would be 0, 1, 2, and 5. Or we could take the intersection, all elements in A and also in B, that's just one element, the 1 in both. Or we could take the set difference. Let's try A less B first. So we're starting with A. And we're taking out the numbers 0 and 1, so that leaves us with 2 and 5. Or we could also take B less A. So we're now starting with 0, 1. And we take out all these numbers. So that leaves us with the 0. Okay, so you'll notice the set difference is not symmetric. The order of the sets matters. It does not matter for the union and the intersection. And of course, the order of sets also matters for the Cartesian product. So if you were to compute A times B, for example, remember A consists of 1, 2, 5. B consists of 0 and 1. So this consists of all tuples where the first element is taken from A. So for example, we could 1. And the second is from B, so we could take 0. Or we could say 1 and 1. Yeah, so those are all combinations with 1 as the first coordinate. Likewise, we can do combinations with 2 as the first coordinate, 2, 0, and 2, 1. And of course with 5 as the first coordinate. So that is the Cartesian product of A and B. And of course, we could also do the Cartesian product of B and A. Is different. So B has the elements 0 and 1. So this first coordinate can now be 0 or 1 only. And the second can be 1, 2, or 5. 1, then 2, 5. And then we can do the same thing with 1 as first coordinate. Okay, so you can see that is definitely different. Okay, so much about sets and set operations. There's one special kind of sets that we'll often deal with, and those are intervals, usually intervals of the reals. So let's have a quick look at those as well. What we have here is we have two numbers, two bounds of that interval. We call us A and B. So for AB in the reals. And we want one of those to be smaller than the other. So let's say A is strictly less than B. We use following notation. We define a so-called closed interval. That means all the numbers between A and B, including A and B, that will be denoted by this notation here. So that consists of all real numbers that are between A and B, and equality is permitted. So that is called a closed interval. We can also have an open interval. We would write the open interval like this, A, B. Or you will also sometimes encounter the notation this, A, B. Yeah, I usually use the first one, but it doesn't make a difference. You're free to use the other one as well. What does that mean? Almost the same thing. The difference is the bounds A and B themselves are not included in this interval. So A is strictly less than any number in the interval, and any number in the interval is strictly less than B. That is an open interval. And of course, we can combine these. We can also do something like A, B, or A, B. And those are half open intervals. And of course, those are exactly what you would expect. In the first case, A is not included, so there's a strict less than here, but B is included. In the second case, A is included, but B is not. Okay, so those are half open intervals. And finally, one special case of this would be to have one of those boundaries infinity or minus infinity. That side by convention is always open, simply because infinity is not strictly a number. So we'd write something like minus infinity to a to denote all x in R that are strictly less a. And of course, we could have made this a half closed interval as well. Now, like for example, here, b infinity, that is all real numbers that are greater or equal to b. And last but not least, one more shorthand for natural numbers. There's a similar thing, not quite the same thing as an interval, but we use a similar notation. For a natural number n, we use this notation here to refer to all natural numbers that are less or equal to n. So more explicitly, this is the set 1, 2, 3, and so on, up to n. And if you want to include 0, we just add 0 as a subscript like this. So that's all I in n0, where I is less or equal to n again. So this is 0, 1, 2, and so on, up to n. Okay, this will sometimes be a handy shorthand. That's why we use that. Yeah, that concludes our pretty long introduction on set notation and set operations. Again, I do hope you've seen pretty much all of that already. But if not, that might be a welcome refresher. Okay, thanks for watching, and I'll see you in the next videos.